Have you ever wondered how your radio can just pull a crystal clear song right out of the air? Or how a TV takes a broadcast signal and turns it into a perfect picture? Well, it's not magic. It's actually a process of sculpting. Today, we're diving into the tiny, brilliant circuits that shape the invisible signals all around us. So think about it for a second. Your television, the radio in your car, and, say, a military radar system. I mean, on the surface, they seem worlds apart, right? One's for entertainment, one's for music and traffic, and the other tracks planes. But believe it or not, they all share one fundamental secret. And that's it right there. They all depend on perfectly, precisely shaped electronic signals. You see, without the circuits that control and mold these signals, all that information would just be random noise. Your TV would be a screen full of static, and your radio would be pure gibberish. So here's what we're going to cover. First, we'll break down what wave shaping even is. Then we'll get into why we even need to do it. After that, we'll look at the two main ways it gets done before we get our hands dirty with the core techniques, clipping and clamping. And finally, we'll reveal where these unseen architects are hiding in the technology you use every single day.
All right, let's just dive right in. At its core, what are we really talking about when we say wave shaping? Well, simply put, it's the process of changing the shape of an electronic signal, we call that a waveform, by passing it through a very specific circuit. Honestly, the best way to think of it is like a sculptor with a block of stone. The raw signal is the stone, and the circuit, with all its little diodes, resistors, and capacitors, that's the chisel, carefully carving the signal into a precise and useful shape.
Okay, so sculpting a signal sounds pretty neat, but why? Why is it so necessary? Why would you build entire circuits just to change a waveform's shape? Well, as it turns out, this isn't just for looks. It's about solving some really critical engineering problems. You see, these circuits are on a mission. Sometimes you need to create a completely new kind of signal from one you already have. Other times, and this is a huge one, you need to limit dangerous voltage spikes that could totally fry your delicate electronics. They're also crucial for just slicing away unwanted junk, like noise, and they can even shift an entire signal up or down. That's kind of like adjusting the height of a loading dock so the truck can connect perfectly. It just makes sure the signal is at the exact right level for the next component to understand it. Now, when engineers design these shaping circuits, they've basically got two main philosophies to choose from: linear and nonlinear. And the fundamental difference between them really just comes down to the electronic parts they're built with. Linear circuits, they use basic components like resistors and capacitors to make really smooth, continuous changes. Think of it like gently sanding the edges of a signal. Nonlinear circuits, on the other hand, they use more dynamic parts like diodes and transistors to make really abrupt changes, and that's what lets them perform the really powerful stuff like clipping and clamping. And this is where it gets really clever. In components like diodes, the relationship between the voltage and the current isn't a nice, steady, predictable line. It's non-linear. And that unique property is what allows them to act like incredibly fast electronic gates or switches. That's the secret sauce behind the most powerful wave-shaping techniques we're about to see. So let's zoom in on those two key non-linear techniques. They are the absolute bread and butter of wave shaping, and honestly, they're pretty easy to grasp once you see what they do. We'll start with clipping. Clipping is, well, it's exactly what it sounds like. It chops off a part of the waveform. A great analogy is a lawnmower trimming grass to a perfectly even height. A clipping circuit does the same exact thing to a signal, just shearing off any part that goes above or below a certain voltage level. So how does a circuit actually do this? It uses a diode, which acts like a little one-way gate for electricity. The circuit is designed so that the gate will only let voltage below a certain level pass through. The second the signal tries to spike higher than that, bam, the gate slams shut and that extra voltage is just chopped off. It's such an elegant and incredibly effective way to protect sensitive parts or just get rid of unwanted noise. The other major technique is clamping. Now, unlike clipping, clamping doesn't cut the signal at all. Instead, it picks up the entire waveform and moves it up or down, clamping it to a brand new starting voltage level. You can think of it like taking a painting on a wall and just moving it higher or lower. You're not changing the picture itself, just its position. But why would you need to do this? A perfect real-world example is an old analog television. The signal coming in carries all the picture information, like brightness, at very specific voltage levels. A clamping circuit's whole job is to grab that incoming signal and lock its baseline to the correct starting point. Without that perfect positioning, the TV's electronics can't decode the picture, and all you'd see is a complete mess.
So when you put all of this together, you start to see that these simple-sounding circuits are truly the unseen architects of our entire electronic world. They are literally everywhere. They're fundamental to our telecommunication systems, they're inside every radio and TV, they are absolutely essential for radar equipment, and they play a key role in converting real-world analog signals into the digital ones and zeros our computers actually understand.
Ultimately, this is the real purpose. They are the critical bridge between the messy, unpredictable signals of the real world and the clean, stable information that our digital technology demands. They take all the chaos and they sculpt it into coherence.
So the next time you turn on a screen or tune in a radio station, you'll know about the tiny, unbelievably fast sculptors working away inside. It really makes you wonder, doesn't it? Now that you know how signals are sculpted, what other invisible processes are quietly shaping the technology you use every single day?